Okay, so another type of question there. Giving you the electron configuration, we need you to be able to identify the element. Which element has this electron configuration? Well, all you need to do is to count the total number of electrons, because total number of electrons equals to the total number of protons. If you know the proton number looking at the periodic table, you will be able to identify the elements there. So we have a total of 16 electrons. Well, 16 electrons means 16 protons. Number 16, we have sulfur. Okay, so given sulfur, we need you to be able to write out this. Given this, we need you to be able to identify the element that particular electron configuration represents. Okay, so here's another example. Which element has the electron configuration of argon 3d10 4s1? Well, argon is number 18. You don't have to memorize this. Argon is number 18. You can look at that information if you're given a periodic table. So number 18 means, well, this particular core notation or noble gas notation, this means we have 18 electrons here. 18 plus 10, 28. 28 plus 1, 29. Who is number 29? Well, number 29, copper. Okay, argon number 18, 29 is copper. So, given the full electron configuration or the noble gas notation, we need you to be able to identify the elements there. So that's what we need you to be able to do. Another type of question related to electron distribution. We can use electron configuration like this, okay? And we can also use what we call the box diagram. Instead of drawing a dashed line there representing the orbital, we put a square in there representing the orbital. Up arrow, down arrow, indicating different direction of spin of the electron. So which element has this particular electron configuration? Well, it's identical to the electron configuration that we're talking about. 2 electron, plus 3, 4 plus 3, 7. Number 7. If you look at number 7 in the periodic table, nitrogen. Okay, so the things in here, that's another thing that you want to consider there. And exam number 3 is going to be a lot of conceptual things. We ask you to memorize quite a bit of information. There's not as much calculation involved in the topics that we're going to cover in chapter 7, chapter 8. Okay, so chapter 6, we may have a little bit of calculation involved in there, in terms of the energy involved in the chemical reaction process. But chapter 7, chapter 8, many of the things that we talk about is conceptual. You just have to memorize what's in there, and there's not as much calculation involved. So in a sense, I would say the third exam is actually easier. But that doesn't mean you don't have to do work. You still have to do the work. You need to do memorization, a lot of memorization. Yeah. Okay, so that's our first learning objective in chapter 8. And what we're trying to do here is that we talked about electron distribution. And that's actually, and in addition to the quantum numbers we introduced, now we know the electron configuration. Now that we know the electron configuration, our next learning objective, we start to talk about what we call the periodic properties. So in the second learning objective, we give you some definition. How do you define ionization energy? How do you define electron affinity? And then in the next learning objective, we're going to look at what are the patterns that repeating itself in terms of electron affinity, in terms of ionization energy, in terms of the size of the atoms, and in terms of the number of valence electrons available. So how do we define ionization energy? That's a D word. Ionization energy, i.e., is the energy required to remove an electron from the atom in the gas phase. And you can forget about the gas phase. You don't have to specify that. As long as you remember energy required to remove electron is ionization energy. Now remember in quantum theory, when we're talking about in the first learning objective in chapter 7, when we're talking about quantum theory, we mentioned the photoelectric effect of Einstein's experiment there. I would say when you shine a light on the surface of metal, sometimes you detect the electrons coming out from the surface of metal. Well, that energy, that light, incoming light, has to have a minimum energy requirement. That energy is what we call the ionization energy. So by definition, ionization energy is the energy required to remove an electron from an atom in the gas phase. So in this case, we use magnesium as our example. Okay, I'm talking about the ionization energy there. Now, this is electron configuration for magnesium. Okay, you have 10 electrons, the core electron. You have 2 valence electrons. 2 valence electrons are marked in red. Okay. Those are the 2 electrons participating in chemical reaction. So if magnesium is participating in a chemical reaction, magnesium being a metal loses electron, according to what we talked about, you end up with magnesium ion, Mg2+, you lost 2 electrons. How much energy does it take to remove those 2 electrons? What happens if you want to touch one of the core electrons? Well, we can take a look at while we do this experiment in the laboratory there, we can actually measure the amount of energy required. So we introduce what we call the first ionization energy, second ionization energy, third ionization energy, and so on and so forth, depending on how many electrons you want to remove. Now the first ionization energy, remember in general, ionization energy is the energy required to remove an electron from an element, okay, from atoms of an element there. So if you start with the atom of an element in the ground state, when you have equal number of protons and electrons there, removing the first electron, energy required to remove the first electron is called first ionization energy. So you go from magnesium to magnesium 1+. This process requires about 738 kilojoules per mole of energy. Okay. Now, going from magnesium plus to magnesium 2+, this process is what we call the second ionization energy, because you are removing the second electron. And accordingly, if you try to remove the third electron, it's the third ionization energy. Now, we're talking about 1 electron at a time. And you start with ground state, 0 charge, going to 1+ charge. And from 1+ charge to 2+ charge, from 2+ charge to 3+ charge. Now, one thing that we do want you to pay attention to here is that the amount of energy is increasing. The more electrons you try to remove, the more energy you have to put in. Okay? So this is an endothermic process. You have to supply the energy in order to remove the electron. And the first ionization energy is 738. Second ionization energy almost doubles, but they're still comparable. So 1451. And if you look at the third ionization energy, it's almost impossible. Too much energy to remove the core electron. That is why magnesium will only give up 2 electrons during a chemical reaction, because the energy requirement isn't really that huge. But if you try to touch the core electron, magnesium will tell you, that's my electron. I'm going to hold on to it. You can take 1, you can take 2. Normally you would take 2 altogether because the energy. If you have 1451 kilojoules per mole of energy there, you may just take both of them. But you don't touch the core electron. That requires a whole lot more energy there. So the conclusion that we can draw here is that by comparing the ionization energy required to remove the core electron versus the valence electron, removing valence electron is much easier. It doesn't require as much energy. But if you try to remove the core electrons it's going to take you a lot of energy there. So that is why only valence electron participate in chemical reaction. Because if you ask the core electron to participate in chemical reaction, the core electron, I need a lot of energy in order to do that.